let's do another example of finding the area between two polar curves. So just as a quick reminder, to find the area between two polar curves given as f of theta and g of theta, what we want to do is we want to take 1/2 the integral from a to b of f of theta squared minus g of theta squared, or the outer curve squared minus the inner curve squared. We're taking 1/2 of that difference from our polar curve area formula, extending that out. Now, we do want to be careful. We want to say that the curve is traced just one time. So when we go from theta equals a to theta equals b, that means that we are tracing the area out just one time. Traced out one time from in between the two rays, theta equals a and theta equals b. So let's take a look at this one. And now on this one, I just jumped ahead and grabbed the graph in Desmos. We've done a lot of graphing with polar curves, so we should be pretty comfortable with the graphing piece of this, so I will skip that in the video. So here what we want to do is we want to find the area that is inside r equals 4 times 4 cosine of 2 theta, which of course is a rose. So we've got the rose graphed in red down below. And then let's grab blue. And then we want to graph also r equals 2, which by the way, that's just a circle of radius 2. And so that is graphed in blue below. So that's a circle with radius equals 2. So we've got those two things graphed, and we're being asked to find the area that is inside the rose but outside of the circle. So the area that we're looking at, let's grab the highlighter, is this area. Now, of course, these polar curves often give us symmetry, and we're going to lean into that symmetry and use that symmetry when we're finding the area here. But we want all of the area that I'm highlighting. So we want all the area that is inside of the rose but outside of the circle. So we want to find all of that, but what we'll do is what we can find, it's the tip of a leaf kind of being cut off by the circle. So if we think of the rose as a flower and these being the leaves, then it's the tip of the leaf that's being cut off by the circle of radius 2. Now, what we're going to do here, though, is we're going to say, okay, let's just call this region 1. Obviously, there are 4 regions that are equivalent. So the total area, so we'll use the symmetry, the total area that we're looking for is 4 times any one of those. So let's go ahead and say 4 times the area of region 1. So 4 times the area of region 1. So let's figure out that area of region 1. And then we'll just multiply by 4 to get the total area. You know, there's actually even symmetry within that. We could actually have cut this up into 8 regions, and we could have found the area of just the top half right there too. Just as a quick note, we'll go ahead and do it the way I first stated since I set it up that way, but there was symmetry even within the region that we're looking at, area of region 1. We could have cut it in half and just found half of it and then done 8 times that region. Okay, so all of that. The next thing that we need to do is we need to figure out, okay, well then what are the rays? And we can actually sort of see them, I guess, on the graph that we did in Desmos. But let's pretend like we had done the graph by hand and maybe it wasn't quite as obvious. But what we need to know is, where is this area being traced out? What is my A and my B? So to do that, we're going to start by finding, I'm going to do that actually down here. We're going to start by finding the intersection points. So what are the intersection points of these two polar curves? Well, when does r equal 4 cosine of 2 theta equal, and then the other one, I guess I wrote r, but when does 4 cosine of 2 theta, when does the rose equal the circle? And the circle was 2. So we're just solving that trig equation. Cosine of 2 theta equals 1/2. And so where's that going to happen? Well, that's going to happen when 2 theta is equal to pi over 3 plus 2 pi, and also at 5 pi over 3 in the fourth quadrant plus 2 pi. So that's going to happen when theta is, let's divide everything here by 2. Let me grab my red pen. Let's divide everything by 2. So that is going to happen when theta is pi over 6 plus pi and 5 pi over 6 plus pi. So, and you can kind of see, obviously, we're finding the intersection points, all the intersection points, and there's an infinite number of intersection points because we're working in the polar coordinate system. So, of course, we can just go round and round and round and keep seeing those intersection points. But we want just where A and B are because we're looking for the area of region 1, and then we're just going to use some symmetry. So for A, when I look at A, we could, like I said, we could actually see that on the graph from Desmos, but I wanted to show you where we're getting that. So where A is at negative pi over 6, and B is hitting at pi over 6, is where the two curves are hitting each other, are intersecting each other. So those are the intersection, the rays at which these two curves intersect. So now let's find the area of region 1. I'll kind of keep it off to the side there. So the area of region 1 is going to be equal to the integral from negative pi over 6 to pi over 6, 1/2 times, now the outer curve is my red curve. My rose is my outer curve, my outer polar curve, and grabbing the blue, my circle is my inner curve. So when we're setting this up, remember we want to take the outer curve minus the inner curve. So when we're setting this up, we want to definitely take that rose for cosine of 2 theta squared minus the circle 2 squared d theta. And we're going to go ahead. I'm going to zoom in so that we can do this integral and, well, actually the simplification and then the integral with a little bit of a closer view. So we're going to get 1/2 times 16 cosine squared of 2 theta minus 4 d theta. Go ahead and distribute the 1/2. So we're going from negative pi over 6 to pi over 6 of 8 cosine squared of 2 theta minus 2 d theta. And then we're going to use an identity. Of course, we got to use that identity to reduce that power right there. So this is going to become the integral from negative pi over 6 to pi over 6. We're going to get 8 times 1 plus cosine of, now it was cosine of 2 theta here. So when I apply the identity, I have to remember to double that. So when I apply that identity, I get 1 plus cosine of 4 theta over 2 minus, not doing anything with the 2 right now, so d theta. I'm going to go ahead and distribute the 8 and the 1, well, I'm going to divide by 2, making it 4, and then distribute. And so we're going to end up getting that nicely simplified into 4 plus 4 cosine. I should have also added the 2, but we'll do that on the next line, or subtracted the 2. D theta. Running into my intersection points there, so I'll shift over just a little bit. Negative pi over 6 to pi over 6. Okay, this is the piece I was saying I should have done on the line above, but that's 2 plus 4 cosine of 4 theta d theta. And now we're all set and we can integrate. So when I integrate, I'm going to get 2 theta. When I integrate 4 cosine of 4 theta, I get 4 sine of 4 theta divided by 4. So, of course, the 4's cancel, and we're evaluating this from negative pi over 6 to pi over 6. And we're going to plug those in, and we're going to get 2. You know what? I'm going to speed the video up here, and you can see me plug those in and get to our final answer. Okay, so here we have it. We have 2, so we have found that the area of one tip of the leaf is 2 pi over 3 plus root 3, and that, remember, is just one segment. That's the segment of segment 1. So if we want the total area is going to be 4 times that. So the total area, let's bring total area over here. The total area is 4 times the area that we found for region 1, which was 2 pi over 3 plus root 3. So it's 2 pi over 3 plus root 3. So that's going to give me 8 pi over 3 plus 4 root 3 for the total area of the region that lies inside the rows, but outside the circles. Let me get that all on the screen right there. And again, I skipped a few steps here because I just jumped right into the graph. Like I didn't actually do the graph. I used Desmos to do the graph. But we could have seen that these were from our families of curves. We would have known that this was a rose and a circle, and we could definitely have graphed it if we had needed to by hand.